Lesson 7-3. Use similar right triangles. By the end of today's lesson, we will be able to successfully use similar right triangles. Theorem 7.5. The proof is given to you on my website. So it states that if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So if I have an altitude drawn from angle C for this big right triangle ACB to the hypotenuse, then it breaks the triangle into two, not only two similar right triangles, but these two right triangles are also similar to its original triangle, right triangle ABC. So let me say this one more time. So triangle CBD is going to be similar to triangle ABC. And triangle ACD is also going to be similar to triangle ABC. And triangle CBD is going to be similar to triangle ACD. And the order of these letters do matter. These letters have to correspond to the right angles. Example 1. Write a similarity statement for the three similar triangles in the diagram and then complete the proportion. So I'm going to first look at the biggest triangle here, GEF. Triangle GEF must be similar to triangle HEG and also similar to triangle HGF. And for the proportion, EF to EG. So EF is the hypotenuse of the largest right triangle, and EG is the longer leg. And EG can also be the hypotenuse of triangle EHG, so that must correspond with the hypotenuse of the largest triangle EF. So I'm going to write EG here. Let me see how this matches. And then EG of the bigger triangle again represents the longest leg of this big right triangle. So I need to look at this right triangle and find out that EH is the longer leg that corresponds with EG, which is the longer leg of the bigger triangle. So this would be EH. Geometric mean. The geometric mean of two numbers a and b is a positive number x such that a to x equals to x to b. Well, there's three possibilities here. CD. When CD is the geometric mean, then the proportion will be that BD to CD would equal to CD to AD. And when CB is the geometric mean, then we have AB to CB, and will equal to CB to DB. And when AC is the geometric mean, we have AB to AC, and then AC to AD. So if we look at this again, the first one, the geometric mean is actually the height or the altitude of triangle ABC, and CB is actually the shorter leg. And AC is the longer leg. So if we look at an example here, we want to solve for y, and we have the hypotenuse here, and it's 9. So I could do 9 to y. So hypotenuse of the big triangle to the hypotenuse of the little triangle here would equal to the shorter leg of the big triangle to the shorter leg of the smallest triangle, so that's 3. So y squared equals 27, and y will equal to 3 square root of 3. So in this case, we used the second case to solve for y. So now we can generalize two theorems. 7.6, the geometric mean altitude theorem. So in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. So again, this is what it means. This altitude here divides the hypotenuse into AD and BD, two segments. And the length of the altitude would then be the geometric mean. This would be geometric mean of the lengths of the two segments, AD and BD. So then we have this proportion here, and so it'll be BD to CD, so shorter leg to longer leg of triangles CDB to shorter leg to longer leg. So I'm going to write short leg to long leg. So theorem 7.7, we have the geometric mean leg theorem, and it also states that if in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments, AD and BD. Then the length of each leg, we're talking about AC and CB here, is the geometric mean. So we have, this is the geometric mean, and this is also the geometric mean. Then the lengths, so this AC and CB will represent the geometric means of the lengths of the hypotenuse, AB and AD, as well as AB and DB. So let's look at the first example here. AB to CB is equal to CB to DB. So CB here is your geometric mean. So that's one case. And then it's the geometric mean of the lengths of the hypotenuse AB, which refers to this one, and the segment of the hypotenuse that is adjacent, which means next to the leg. So this part is a segment of the hypotenuse AB, and it's next to the leg CB, which is your geometric mean. So that's why we have this one here. And so the same goes for the other one. AB to AC is equal to AC to AD. And AC here, this is your other geometric mean. And it is a geometric mean between the hypotenuse AB and the segment of the hypotenuse AD, okay, and that is adjacent next to the leg. So this leg again refers to the geometric mean. So it's really important that you memorize these three proportions. So example 2, we're going to look at a few examples of how to use the theorems just explained. Find the values of the variables. Okay, so for the first one, I need to use the geometric mean altitude theorem. 8 plus 5 over 12 equals 12 over 18, and then I can simplify this. So A plus 5 equals 8, and A equals 3. Okay, and for this one, we can do 8 over 6 equal to 6 over B plus 3. Simplify. And B will equal to 1.5. Okay, for the next one, we can use the geometric altitude theorem, 16 to 12, which equals to 12 to x. So x would equal to 9. And now that you know x equals to 9, then the hypotenuse of the biggest triangle will be 25. And then I can use geometric leg theorem to find y and z. So let me do y first. So that will be 25 to y, and then y to 9. So y would equal to 15. And then the next one will be 25 to z, and then z to 16. And 25 times 16 is, so that's 400, and z would equal to 20. Example 3, use the geometric mean theorems to find AC and BD. So in this case, we're going to have to first use the Pythagorean theorem to find AC. So that's 20 squared plus 15 squared equals AC squared. So AC equals 25. And then I can do, let this be actually X and Y. 25 to 20 goes 20 to X. So X equals to 16. And then 25 minus 16 will be 9. So then I can solve for BD now. 16 to BD equals BD to 9. So BD squared, 16 times 9 gives me 144. And BD would therefore be 12.